So now that we've covered directivity and efficiency, antenna efficiency, we can move on to what is often considered the most important parameter for an antenna, which is the gain. And the gain of an antenna is the ratio of the radiation intensity in a given direction to the radiation intensity that would be obtained if the power accepted by the antenna were radiated isotropically. So the radiation intensity corresponding to an isotropically radiated power is equal to the power accepted by the input power divided by 4 pi. So gain is therefore defined as, give it the symbol capital G. It's again a function of theta and phi. It's equal to the radiation intensity divided by the power accepted by the antenna, so we'll call that P in, and that's divided by 4 pi because it would be as if it was radiated isotropically, so we're spreading that over those 4 pi steradians in a sphere. And so again, we just flip that 4 pi into the numerator, and we get the standard definition for antenna gain, which is 4 pi times the radiation intensity in a particular direction divided by the input power. So what is this input power? And we'll address that by using the concept of efficiency. And on the last slide, we saw that antenna efficiency relates the power input to an antenna to the power radiated by an antenna. We said that the efficiency of the antenna is equal to the radiated power divided by the transmitted power, or the power input to the antenna. So this allows us to use efficiency to calculate gain with one caveat. Gain calculations do not include losses arising from any impedance mismatch or a polarization mismatch or any other types of mismatches. So when we calculate efficiency for gain purposes, we're only going to include the effects of antenna radiation efficiency, that ECD. So we get that power radiated by an antenna for purposes of gain calculations is equal to radiation efficiency of the antenna times the total power input into the antenna. And so now we can substitute that into our gain equation, and we get gain of theta comma phi is equal to the radiation efficiency of the antenna times 4 pi mu of theta comma phi over that P rad there. Right, so we've made that substitution, and you might say, oh wait, I recognize that. That's the directivity of the antenna. Okay, so we've got that directivity in there, so all we have to say now is that the gain of an antenna is equal to the efficiency of that antenna, only including intrinsic efficiency of the antenna. We're ignoring polarization, we're ignoring reflections due to antenna mismatch, times the directivity. And so gain is just like directivity, but we're also accounting for the efficiency of the antenna here. So just like for directivity, we're often concerned with max gain. We don't really typically care about the gain in any direction. We're concerned with gain in a specific direction, usually the max one, so we call that G max. Some people again call that G0, the max gain. And it's just the maximum value of the gain function. And so that's just going to be equal to the antenna efficiency times D max, which we discussed in pretty much detail in a previous video, so I'm not going to go over it too much. So since gain for an antenna is calculated using this substitution for an isotropic emitter, it's usually specified in what we call dBi, decibels isotropic, or decibels reference to an isotropic emitter. And so what we do is we say gain in, or G in dBi, gain reference to an isotropic emitter, that is just equal to 10 log of the gain that we calculated in this manner up there. So Sometimes, however, you will see gain figures in units not dBi, but instead you'll see them in units of dBd, which is gain as compared to a dipole antenna. And so both of these make sense because dB calculations are based on ratios, and these are relative measures. So we can calculate gain range as according to a dBi, which is an isotropic emitter, or we can calculate it as compared to a dipole antenna. So here I've got some common gain ranges for different antenna types: dipole, whip, etc. And so this tells you basically how efficiently an antenna points in a certain direction as compared to how much radiation would exist for a similarly powered isotropic emitter. And that's what gain is telling you. So it's simultaneously telling you two things. It's telling you how directional antenna is, and then it's also taking into account the efficiency of that antenna in converting energy into radiation. So that's why gain is such an important factor. So when you're evaluating the performance of an antenna, when you're looking at antennas for different design applications, you need to be careful to consider the reference here, and you got to consider if it's using a reference of a isotropic emitter or if it's using a dipole antenna as the reference. For the same antenna, we can see that the gain in dBi is about 2.15 dB larger than it would be in dBd. And so the table on this slide is just listing some gain ranges when you're evaluating these common antenna. And one thing I want to point out is that the term gain, it's sort of confusing when we talk about antenna because they're passive devices and therefore they actually don't, amplify power in a circuit. Let's say we have an antenna that's got a gain of 8 dBi. What we mean by that is that in the maximum direction of radiation for the antenna, 8 dBi more EM radiation is transmitted as compared to a similar isotropic antenna. So if we say we've got 8 dBi of gain, what we're saying is that the distance from here to here is 8 dBi, right? That comes at the expense of the fact that this isn't emitting power in other directions. So the gain in this direction, for example, you'd have a negative gain, minus infinity right there. So, and that's why we usually talk about gain in terms of the direction of maximum transmission. Also, if you're looking at other resources in this class, if you've got a supplemental text or something, you may see gain defined in terms of normalized power or normalized power density instead of radiation intensity. And so because they're normalized, it doesn't matter which one you use, as I pointed out in a previous video. But a lot of times what you'll see is that gain is defined as the normalized power density function for the antenna that you're interested in looking at divided by the normalized power density function for whatever your reference antenna is. So that's another way to define it. The math works out to be exactly the same, so you can do this derivation either way. I just prefer using radiation intensity.